We started talking about the Wittig reaction, this idea of using ylids and using nucleophilic species on carbon. So we started out with this and we said, all right, we can take a phosphine and we can attack an alkyl halide and we can do an SN2 reaction. And that's limited to, let's say, methyl groups and primary systems and some secondary systems. T-butyl groups and tertiary systems are not good here. Why not? If it's an SN2, it's too sterically crowded. And we'll see when we build this thing in a second that if you have a tertiary system here, there's no proton there to take off, so you can't make an ylid. So you at least have to have a secondary system to have a proton there that can come off in the second step. We have the formation of a phosphonium salt. This thing is polar. It tends to precipitate from solvents like ether or THF, and that's very convenient because you can filter it and dry it, and then you're away to start the next step. The phosphonium salt is then suspended in some solvent, and you can add some strong base. I'll show you in a second. N-butyl lithium is very good at this. Take off that proton. And this is the first example, probably, of having a carbon next to a powerful electron withdrawing group that helps stabilize the negative charge in the conjugate base. This wouldn't happen if it was just methyl bromide or something like that. It's going to happen if you have something positive next door. So the base comes in, takes off one of these protons, and we end up with this species. And it's somewhere in between these two structures. And the reason we have to draw two resonance structures is because the charge really isn't localized on C, but it's not completely separated into a double bond. We can see now that because phosphorus is quite large and because carbon's fairly small compared to it, the orbitals just don't match. The neighboring orbitals don't match too well, the overlap isn't great, and we don't get a full bond. Now, the resonance structure on the left is very useful because it does show now we have a nucleophilic carbon, but this one here shows you that you do get some stabilization. And that's the rationale behind why you can take these protons off these carbons where we couldn't do it with earlier examples. So once we have the ylid, we can start thinking about what to do with it. You will mix aldehydes and ketones with the ylid, and you may have to make the ylid from the phosphonium salt. That's something I expect. And what you're going to do here is swap out this oxygen for the carbon. So whatever is attached here basically goes where the oxygen was in the ketone or the aldehyde. That's all it is, a straight swap. Now that's fairly powerful because you can direct the ketone, or I'm sorry, you can direct an aldehyde or a ketone to give you exactly the alkene that you want. The alkene will go where you tell it to. Again, here's the book sort of picture to show the delocalization. The structure is somewhere in between, and if you wanted to draw this picture, you'd certainly have to think of it like this. This is delta negative, and this is delta positive. So this is a powerful carbon nucleophile that we can use now to make alkenes. So mechanistically, this is typical of a sort of one of those 10-point exam questions where you're given a starter material, you're given a product, and you're given some reagents, and you have to fill in what's in between. And to do this, we'll think about the first step. This looks like a primary alkyl halide. It's benzylic. So it's activated for these types of things, and we'll do this. We'll do an SN2 reaction, and that will give you, ultimately, the phosphonium salt. In the lab, you isolate that stuff, you make sure it's the right material by NMR, for example, take its melting point, and then we have the proton next door is now more acidic than it was because of the positive phosphorus. And we use a powerful base like N-butyl lithium, come in, take that proton, and we produce the ylid. And again, keep an eye on the questions as they're being asked. If it says draw resonance structures, you need to show both resonance structures for that species. We typically use this one to describe the next step because it looks like the carbon is nucleophilic. So then we'll put an aldehyde or ketone in there and we'll go after it. The only difference in this reaction, as far as you are concerned, will be the substrates. They might have different shapes, they might have different cycles, they might be acyclic, but the chemistry is the same every time. We have nucleophilic addition on the delta positive carbon by the negative carbon here, and we form a carbon-carbon bond. That's the first bond that gets formed. We'll be doing a lot of that over the next 2 weeks. Now this species here is sort of indicative of how strong a phosphorus-oxygen bond happens to be. We've got some bonds in nature that are very, very strong, such as silicon-oxygen bonds, such as phosphorus-oxygen bonds. And what's going to happen here, along the pathway, if you look at the oxidation state of phosphorus at the beginning, it's +3. It's bonded to 3 carbons, so it's a 3-valent phosphorus. Ultimately, the phosphorus will want to be 5-valent. It's one of these atoms like sulfur that can expand its octet and give you different valencies. And we'll see now that the driving force for this reaction, the reason why it goes, is because phosphorus wants to have 5 bonds, and it particularly wants to bond to oxygen. So what will happen now is that this will go after the phosphorus, and we'll form this cycle. It's worth it because you get the phosphorus-oxygen bond, but on the other hand, it's not so good because it's a 4-membered ring that contains a big phosphorus. So it won't last very long, but it can be formed sort of transitory. There's what we call an oxaphosphatane. If you remember the name, great. If you don't worry. It's a 4-membered ring that won't last very long. And how it's formed is that we've brought these 2 pieces together like this and this to form a box, or to form a 4-membered ring. How it will break is different. How it will break is in the opposite direction. So you brought the things together like this, and then you're going to break them like that. That's really what's happening. And again, the motivation, or what I call the driving force for this, is again the formation of a second phosphorus-oxygen bond. I've got one phosphorus-oxygen bond right there. If I let this reaction go, I will get a second, and there's my second PO bond right there. So we went from phosphorus 3 to phosphorus 5. I don't think you see phosphorus 3 in nature, and you can see now the driving force of that process. So know this one. This is important. This is something you will see for sure in an exam at some point, and it's an important way of putting alkenes together. So examples. You can now start to think about doing retrosynthesis, and you can start thinking about putting systems together to make more complex products. You look at these alkenes, they're not that complicated, but they do sort of exemplify the things I'll ask you. And if you think about this in a synthetic sense, how do I make this double bond? Well, typically what we've done is add a grignard to a ketone to make an alcohol, then do dehydration, and you end up with a double bond. But that's governed by Zaitsev rule, which typically gives you the more substituted double bond every time. What if you don't want that? What if you want your double bond someplace else that isn't the most stable outcome? Well, you can use the Wittig reaction. And what we can see now is we can split this double bond in two different ways. We can split it so that the top becomes the aldehyde and the bottom becomes the nucleophile, or vice versa, where the top is the nucleophile and the bottom is the electrophile. And it's your choice. In terms of experience, I would argue that this one is easier. Okay? You'd have some problems maybe making this species because it's a secondary alkyl halide to start with. That's crowded. It will be a slower reaction with the phosphine, and maybe this negative charge isn't so stable. But over here, that's easy to make, and acetone is dirt cheap. You know, acetone is very cheap. You use it all the time in the lab. So what we have here are two different syntheses of the same molecule, starting with different materials. If I start with the secondary bromide, you can make some comments about how fast this will happen. It will be slower because it's secondary. And once you get to the phosphonium salt stage, maybe the proton isn't as acidic because it's on a secondary carbon. But same sequence. Make the salt, go after it with a base, add the carbonyl. Mechanistically exactly the same as the previous slide. On the right-hand side, I'm starting with the methyl bromide. That's very easy for an SN2, right? That's the best sort of substrate for an SN2. And so we can add the phosphine, we can go after it, we can kick out the bromide, make the salt, bring in the base, bring in the aldehyde or the ketone, and we get this product. So study it and be able to use it, because now we've opened things up. We've got new methods now to make bigger molecules, and we can start doing really what's important here, carbon-carbon bond-forming reactions. So here's a challenge. You're given this molecule, and you might be given a list of possible starter materials limited to those compounds, and you have to go into the lab and build this material. So the double bond is the obvious place to focus on. I'm not going to make that bond. I don't know how to. Okay, I'm not going to make this bond. That seems silly. Maybe I can make a six-member ring by a Diels-Alder reaction, but I'm going to go back to cyclohexyl systems and cyclopentyl systems. If I break this here, I have two choices. I make this the nucleophile and this the electrophile, or the other way around. Sometimes one is easier than the other, sometimes they're just the same. So in this system, I can start with the cyclohexyl bromide, make the salt, take off the proton, add this ketone, and put the two pieces together. On the other example, I can start with a different bromide, do the same sequence of events, and have the other part of the molecule come in as the ketone, and snap the two pieces together. So this is very much like molecular Lego. You're just taking the blocks and you put them together using the rules. So we're talking about chemists with interesting names. This is Baeyer-Villiger. This is an oxidation. And this is kind of a unique reaction at this stage of the game. This is mimicked in nature. I should say that carefully. We mimic this reaction from nature using the Baeyer-Villiger reaction. So this is a reaction that involves one of these things, and we haven't seen these for a while. We did see them a while back when we did addition of oxygen to alkenes to make epoxides. And we use things like MCPBA, all right? I'm not sure I have a picture of MCPBA, so I probably should draw one. MCPBA, if you remember, benzene ring. We have a chlorine at the bottom, at the meta position. And then up here we have a carbonyl next to an oxygen. Starting to look like a benzoic acid, but it has an extra oxygen. That's where the peroxy part comes in. And if you remember back to last term, whenever you put O next to O, that's a weak bond. You'd rather break that bond if you can along the reaction profile someplace. So that's exactly what we're going to do. We're going to use this reagent to deliver oxygen to this ketone. We're going to end up with an ester, and then we'll end up with a more stable benzoic acid product. So this is key. I mean, if we're doing synthesis, this type of overlap between the families is really, really important. We're starting off with a ketone, and we are producing an ester. If we're starting off with a ketone, it's electrophilic. This guy has to be nucleophilic, and we end up with that. So what's happened here is oxygen has found itself into a carbon-carbon bond. This is a spectacular reaction. Again, the motivation here is to get rid of this OO bond. And fortunately, if we put that in the presence of a ketone, we end up with an oxidized material. This is one of the very few ways you can actually oxidize a ketone. You think about oxidizing alcohols, we went from aldehydes to carboxylic acids, but we always said ketones don't go very far. Now we can do this. We're going to oxidize this material, and away we go. So what will happen here, and I'm going to explain this in a bit more detail in recitation, but I'm also going to point you to my mechanism on the website there, because again, I think what happens first is protonation of this species. If you protonate this thing, you set it up for a nice nucleophilic attack. Let's face it, this isn't a very strong nucleophile. But if you protonate the carbonyl, you can make that carbonyl more electrophilic, and therefore nucleophilic addition should be faster. And what we get is this guy. And this is no more complicated than what we saw a while back when we did, for example, the hydroboration oxidation sequence, where you saw migration. So somehow, you have to insert an oxygen into that carbon-carbon bond, and that involves this bond breaking somewhere, and it involves this R group migrating to oxygen. We saw that with hydroboration, so you've already done this sort of thing. Once we get to this intermediate species, again, what's happening here? What is this step right here? Well, it says so, doesn't it? Proton transfer. I'm getting a proton jump from one oxygen to the next. Why do I do that? Why? You know, many of you have been in recitation this week. What was the whole point of these proton transfers? To set up leaving groups, to set up leaving groups. That's exactly the same thing that's happening here. This thing is going to want to be a leaving group if it can. So this is where the magic happens. The O from the carbonyl comes back down, and we kick out to this, we migrate to this oxygen, and we kick out this leaving group. That's the key step. It's on my website with those mechanism videos. I think it's a more clear explanation there. And you'll find now that whatever the R group is here ends up on the oxygen, and that happens to be an ester. Mechanistically, something different. But again, if you take biochem, this is in there. This is something that you'll be seeing again. So it's a migration from carbon to oxygen. And the benefit of this, or the reason it works, is to get rid of the OO bond. We need to worry about outcomes. We need to worry about how to turn ketones into esters. And you'll see now some sort of interesting examples of regioselectivity, when things happen and where things happen. In the top example, I'm taking this peroxy acid, and I'm taking a ketone, which happens to be symmetrical. That's important right now. And I'm turning it into what we call a lactone. Now, a lactone, for future reference, is nothing more fancy than a cyclic ester. Okay, a lactone is a cyclic ester. And you can see now that if I'm using a cycle and I do a migration step and I include an oxygen into this system, the cycle has to get bigger. And it only ever gets bigger by one atom. Never two or three, only by one, and it happens to be the oxygen. So this lactone here now is the ester. You can see here carbon, carbonyl, oxygen, carbon, that's an ester. And this is a very, very simple, elegant way of doing this. Just for reference, you'll see sometimes the solvent is included, CH2Cl2. So now insertion into there gives you a lactone, one atom bigger. Very useful to go from the ketone family, which does nucleophilic addition, to the lactone family, which eventually will do nucleophilic acyl substitution. Okay? So those are going to be very important, and there's a nice, easy way to get there. Down at the bottom, here's a little trick. Here's a question that's making you think and remember and use some rationale here, use some logic. In the mechanism for this process, I'm migrating to an oxygen. And that seems to be a lone pair or a pair of electrons from the R group going towards the O. So what is the R sort of behaving as? It's moving across and it's taking electrons with it. It's kind of nucleophilic. Yeah? It's kind of moving with its lone pair. So I'm going to say that the more nucleophilic this piece, it's more likely to move. So you have a choice here between inserting into this carbon-carbon bond or inserting into that carbon-carbon bond. Exclusively, it goes there. So this is regiochemical. This is a regiochemical outcome now. And the answer is because in the migration step, this group is more electron donating than the methyl group. So the more electron donating group goes first and faster than the lesser donating effect. So in this case, if you have a T-butyl group, it will go first. If you have an isopropyl group, it will go next. If you have a methyl group, it will go last. And that's sensible. That's common. So we have a very powerful method now for making esters from ketones. I've got a few more examples. Top system, no problem whatsoever. Everything's symmetrical. All you have to worry about is inserting an oxygen into one of those CC bonds next to the carbonyl, not further down the chain. MCPBA is just the abbreviation for the structure I drew with the peroxy acid. And then CH2Cl2 is just a simple solvent that works very well for this. No problem with that one. Down here, 5-membered ring becomes 6. You insert one atom, you get a 6-membered outcome. MCPBA here, again, same conditions. There's the lactone. You need to know that one. You need to be okay with it. Now, at the bottom, again, people who are looking to get A's in this class and go on to graduate school or professional school or whatever, these are the types of questions you should be comfortable with. What has happened here is the insertion has occurred on the side of the more highly substituted carbon. This carbon here is more highly substituted than this carbon here, so it migrates faster. But something else has happened. There is also a clue in here, something that should trigger something off about the mechanism and how it's happening. What is the outcome there of the stereochemistry? It's the same. What's the word we use for that? Say again? Conservation. There's also another word we use. Retention, right? Retention of stereochemistry. It's retained. Now, what does that tell you about the mechanism, typically? It's concerted. Absolutely, it's concerted. So you put that little bit of information right there against that mechanism from a couple of slides ago, that whole thing is concerted. And there's some evidence for it. So the Baeyer-Villiger reaction is the use of an oxygen nucleophile to set off a very impressive carbon-carbon bond rearrangement to give you an ester. And I've said this a couple of times now, we are going between the families. Aldehydes and ketones are a big family. Esters and carboxylic acids are another separate big family, but you can relate them. You now have an awful lot of the toolkit required to do organic synthesis. And in the next couple of weeks, the toolkit to do bioorganic synthesis and biochemistry. So I can say now in chapter 20, we covered an awful lot of carbonyl chemistry that we saw previously. And we know how to make these things, and we know how to use them. Okay? In this chapter, we saw Wittig chemistry, we saw acetal chemistry, we saw thioacetal chemistry, stuff like that. We made imines, we made enamines, we hydrolyzed them, and then later we'll use them. How do we get there? This is the problem now. This is like taking a course in Japanese and you learnt words 20 weeks ago that you haven't used since then, and you've got to go back and remember what they mean. You've got to start using them again. So in this example, we can make aldehydes and ketones from alkynes, we can make alkynes from alkenes, we can make alkenes from alkanes. We're completing the loop here. And we can see here we have an alcohol, which obviously can go to an aldehyde or a ketone through oxidation, and we can also turn any of these materials into very powerful electrophiles or nucleophiles. So at this stage, you should be happy with that slide. If you're not, you've got to spend some time on it, because you'll be seeing questions from now on that include material from the entire 2-semester sequence, stuff that we haven't seen for a while. You need to know how to do it. So here we go. In terms of the rest of the course, 2 major things to do. Carbon-carbon bond forming reactions, and then putting it together with all of the functional group manipulations that you've already seen to do synthesis. And so we can see here from that chapter, or actually from chapter 13, we know how to make these bonds, and you've done that in the lab. You know how to make a Grignard reagent, you know how to add it to an electrophilic species, and we can end up with a more complex material by doing nucleophilic addition. You now know how to make cyanohydrins. Not that useful to us, but it's an example of a CC bond forming reaction, so that's why we put it there. And I think the most important one from the previous chapter, the one that we've just finished, is the Wittig reaction. That is absolutely very powerful to be able to manipulate and make more complex molecules. So keep an eye on those things. Now, in terms of doing the synthesis, again, recitation is a good place to practice. Office hours are a good place to talk about these things if you like. But this becomes fun. If you know this stuff, it's now time to use it. And I would argue that, unlike a lot of other subjects, you can take this stuff and do new chemistry very quickly. You could find something that hasn't been done in the lab based on what we do here and go do it. A lot of other subjects, you're just learning what's been done. Here now we can do new things. So in this example, what's happening is we're taking this material here, and that could come about from this ketone here by a Wittig reaction. You start out with cyclohexanone, and you get yourself a Wittig reaction to make that material. And what did we use instead of this BH3? 9-PBN, the parachute, right? And that whole sort of regiochemical argument based on steric environment. And then we did a rather complicated oxidation step, which is very similar to the Baeyer-Villiger reaction that we just did. So put them together and see that. And that gives you the primary alcohol. Now, this reaction with PCC, I think most people are happy with that. We make an aldehyde. Why does it stop at the aldehyde? Why not go to the carboxylic acid? What's missing from this mixture? What do you prevent from being in the mixture? Water, because water gives you a hydrate. And again, in recitation, we put all this together now. If water gives you a hydrate, that hydrate oxidizes. You now know how to make the hydrate. Here you stop at the aldehyde because there is no water. Then you do nucleophilic addition followed by a quench, and you've got yourself a secondary alcohol. And once you've got a secondary alcohol, you can make a tosylate, you can eliminate, and you can make a more complex alkene. You can go a lot of different places. That is a good thing if you like this stuff. It's a nightmare if you don't. So here we go. This is an example of synthesis in which half the class might get one method and half the class might get a different method. And on paper, everything works. Okay? And on paper, this is fine. This sequence here is fine, but this sequence down here is probably shorter. It's probably more economical. And that's why chemists still are employed. You know, we've always got some way to better what we've done before, to improve what we've done. So in this example with 7 steps, great, if you enjoy doing 7 steps. But down here I've got 3 steps. So now the Wittig chemistry maybe takes out some of the old chemistry where we did alkene synthesis, and Wittig allows you to do it in a very, very quick manner. I would say on my exams, if you're dealing with 7 or 8 or 9 steps, you probably went wrong somewhere. Usually these things are not more than 4 or 5. I've seen some elegant syntheses with 10 steps in them this past couple of weeks, but they're probably not the easiest way of doing it. But people are getting it, but people are starting to understand. Okay, IR, go back and look at this stuff. Again, we can use this as clues on an exam. The aldehydes and ketones, we've got unique sort of absorbances in the IR spectra. We've got slight differences now depending upon conjugation. I'll come back to this later. That double bond there is special. That really is a special double bond. You will love this double bond. And down here we've got some differences in terms of the strain in the cycles and the sp2 hybridizations and stuff like that, but they're all roughly in that region that you know about from that spectroscopy sheet. Here we can see, just to finish off, just to wrap this up, how do you know it's an aldehyde? Well, if you have an IR spectrum, you can see the signal here for this CH bond, and you also know we have it down there. What's the easiest method to find an aldehyde in a sample? What's the easiest method you know, knowing what we've done? No, it oxidizes to a carboxylic acid, but spectroscopically, what's the piece of data you want to tell you that you've got an aldehyde? NMR spectrum, right? Down about 9 ppm. So you've got lots of possibilities now to work out these structures. So in the proton spectra for aldehydes and ketones, again, look back and look at the fact that you can put protons next to a carbonyl, alpha to carbonyl, and they show in a certain place, and that gives you a clue as to what you've got. So that chapter, all about aldehydes and ketones, I think is a good place to get to now, because it summarizes a lot of where we've been to let us go somewhere different. So here we go. My favorite slide in this chapter, that one. That's where you are at, or that's where you should be at if you want to pass the class. There's a lot of stuff there. So keep an eye on that. We have said that aldehydes and ketones are central to everything. And before that, listen to this. Alcohols were central to everything. And that should make sense, because how do you make aldehydes and ketones? From alcohols. So now you've got this whole sort of picture where alcohols can be turned into aldehydes and ketones, and aldehydes and ketones can be turned into this lot. And that's an impressive array of reactions. So the toolkit is getting bigger. You'll have to buy a truck. You want to carry it around. You know, my job is to keep you on course and to keep you confident and to try and keep you recognizing that we're just building. We're just adding on to things. There isn't an awful lot of new chemistry to come between now and the end of term. It's just using the same ideas. And you've got to keep focused and keep disciplined and make sure that you are keeping up. Shifts focus from the aldehydes and ketones, which do not have a leaving group, to the carboxylic acids and their derivatives, which do have a leaving group. That might be worth writing down several times. Like on quizzes this week, protonate something if you have protons. Like on quizzes next week, deprotonate something if you have bases, things like that. So far we've done carbonyl chemistry where we attack the carbonyl. Now we have the possibility of something breaking off. We have a leaving group attached. So this slide is just showing you the sort of, where do you find things like carboxylic acids. And then, this is very sort of misleading here. It's almost a sort of a throwaway. Carboxylic acids and their derivatives. Except carboxylic acids and their derivatives is a huge chapter, because there are many of these derivatives. So we've got some examples here. You know, you leave a bottle of wine open, it will go sour, eventually becomes vinegar, and that's kind of where that is. Butanoic acid smells like rancid butter, apparently. The butanoate type compounds do stink, I do know that. Hexanoic acid apparently is for the odor of dirty socks. I wouldn't know because I do laundry every day. But apparently that's got a really nasty smell. And then lactic acid, we know that from milk, and we know that from exercise, right? Lactate builds up and stuff like that. Acetyl salicylic acid, aspirin. I think you've already seen this on an old problem set somewhere or an old exam somewhere. That thing has an ester and a carboxylic acid group right there. And then this stuff here, which is 4-aminosalicylic acid, there's the carboxylic acid. What's its pKa approximately? Yep, towards 5. And then we have this, which is a phenol. What's its pKa? about 10. And what about this thing here? Be very careful. Everybody wants to say 38, right? I think it's lower than 38. Why is it lower than 38? Resonance stabilized when you take off the proton. Simple things. And then we get into some of these things which are starting to look like vitamin A. I can't even say that one. Isotretinoin. Good luck to the pharmacists. Carboxylic acid at the end. Very close relative to vitamin A. Maybe it gets metabolized to vitamin A. But we can see now carboxylic acids are very useful and they're all over the place. Nomenclature, same as usual. I'm not going to spend a lot of time on it because it's something you can pick up. It's a clue here. Oic acid, oic acid. Now that little word acid, right, that's a clue. If it's got the name acid in it, it'll probably be an acid, okay? So it can be deprotonated. And watch out for that type of thing. It's facetious to say so, but you'll be amazed on quizzes and exams how many people forget the fact that the word acid there is a clue. And they don't deprotonate these things. So we've got butanoic acid, a more complex one here, 5-hydroxy-4,4-dimethylpentanoic acid, which I think you can get from the longest chain is 5 carbons. The oic acid tells you the fact that it's a benzoic acid, or it's a carboxylic acid. The 5-hydroxy now tells you that the OH is subservient to the carboxylic acid. The carboxylic acid is the major functional group. And the 4,4-dimethyl is simply because of this. And again, we got some issues here where the longest chain doesn't quite make sense, and that carbon here isn't part of the cycle. So we're going to call it cyclohexane carboxylic acid. Similar to the benzaldehyde stuff. Down at the bottom, we have different ways of saying this. We could call this, if you like, methanoic acid. It's got 1 carbon, so it could be methanoic acid, but if we calls it formic acid. This could be ethanoic acid, acetic acid. This could be propionic acid, exactly that. And then butyric acid and benzoic acid. So they're fairly simple, nothing more complicated than anything we've seen so far. Dioic acids. Now we're getting technical, now we're getting complicated. We can start to make polymers now, if we start to make difunctional groups. We can see here on the molecule we have 2 carboxylic acids, that's where the di comes from. Oic acid, again at the end, just tells you it's a carboxylic acid. Down here, oxalic acid is a kind of a unique one. It's got 2 of these things directly attached to each other. Malonic acid you will see a lot of in the last few chapters. This is very useful in synthesis. Succinic acid is important in biochemistry. Glutaric acid is important in biochemistry. Those are common names that you'll learn as you go along. Succinic tends to be 4 carbons, malonic is 3, and then glutaric acid is 5 carbons. We'll touch those again when we do polymer chemistry in the near future, but again, the nomenclature makes some sense, I think. Physical properties. A little bit more here than we had with the aldehydes and ketones. It's not quite as clean as, or as simple as it was with the aldehydes and ketones. We have lone pairs on this neighbor now. Number 1, this can leave. One of the problems with carboxylic acids is that they're quite high boiling points. A lot of the idea of the high boiling points is the fact that they have this nice hydrogen bonding setup where they're bonding twice. So you can see here now we have a hydrogen bond across and a hydrogen bond across there. Anybody who's taken genetics, what does that remind you of? DNA. Yeah, you're starting to see DNA sort of system. You're starting to see base pairing across a system. This is the beginning of that. In terms of their physical properties, this should be logical now. If they have stronger hydrogen bonding possibilities, they should have higher boiling points than molecules that are closely related to them. So acetic acid here, which is not, vinegar is acetic acid dissolved in water, so that's a mixture. But acetic acid itself has a high boiling point of 118, whereas ethanol, very close to it, has a boiling point of 78. And that additional 30 degrees or so is because of the extra hydrogen bonding possibilities, which are shown right there. Easy enough. Now, at the end of this class, you absolutely have to be happy with acid-base chemistry, or else you wouldn't have gotten through. You absolutely need to know about acid-base chemistry, so when you move to biochem, you're okay with it. We have now, going back all the way to the first week, that was a long time ago, carboxylic acid, pK of roughly 5. Base, you know it's a base, it's hydroxide, it always was a base. We can take off those protons, we can make salts. In terms of pKa's, there is a slight difference now. We probably do have to be a bit more detailed. They don't all have exactly the same pKa. They're certainly not all going to be exactly 5. In the system above, 4.19. We might say that this benzene ring is electron withdrawing. Here, 4.76. That's typical of the sort of 5 number that we've been talking about. 4.86 is typical of that number. But we can make some differences here where we add some quite electron withdrawing groups, quite powerful electron withdrawing groups, and that gives you quite different acidities. So what I'm looking at here, down at the bottom, don't forget roughly 5, but compared to alcohol is much more acidic because of the fact that we can delocalize. The difference now is we can delocalize in a carboxylic acid salt that we can't do when we take a proton off an alcohol. So most of this is FYI. I want to get into the mechanisms. Look at this. Acetic acid itself is approximately 4.8. That's a decent organic acid. You put a chlorine on there, it drops. Has that become more acidic or less acidic? It's more acidic. Why is it more acidic? What's the chlorine doing? It's withdrawing electron density. It's taking electron density away from its neighbors. That will have a little effect on this proton. It'll make it more positive. But when you make the anion, the conjugate base, it will also help share some of that charge. The electron withdrawing ability of that neighboring group will help share the charge around better through the single bond system as well as the pi system, and you'll end up with a more stable anion, which then constitutes a more acidic conjugate acid. Likewise here, you put two of these things on. 1.9, that's quite low. 0.3, sorry, 0.9, that's quite acidic. You put 3 chlorines on there, all of a sudden this stuff becomes quite dangerous. You've got to be careful with these things now, it's caustic. Down at the bottom, look at the differences here. What is happening here? What is happening in those different systems? It's getting further away, and the effect is dying off. If you have the electron withdrawing piece very close to the carbonyl, sure, you're looking at quite a dramatic. Don't forget pKa is a power of 10 scale. So in this case, we're looking at this being quite more acidic than the one above it. This here is becoming less acidic because the chlorine's getting further away, having less of an effect on the OH group. And then further away again, it goes back to being a normal carboxylic acid. So that effect dies off, which I think should make sense. Other systems, just brought this in to just sort of make you think. You have seen these things, and you should be okay with this from the benzene chapter. We are positioning some group at the end of this benzene ring, and we're looking at the effect of this thing on the pK over here. Now, you cannot really delocalize into that system. If you put a negative charge there, it's not going to be able to delocalize into this system. It's going to delocalize between here and here. But even having said that, if you have a nitro group at one end, its pK is 3.4, and if you have a hydroxyl at one end, its pK is 4.5. What is the big difference between this group and this group? Absolutely. Nitro group is electron withdrawing powerfully. That's why it's a meta director. And the OH group was an electron donor. That's why it was an ortho-para director and an activated benzene. Same principles, same ideas. So in between, electron withdrawing, a little bit of electron withdrawing, neutral, you would say, electron donating, electron donating. There's a definite pattern there. And at the bottom, same type of deal, just changing the place of this thing around the cycle, putting it in the ortho or the meta or the para position, and you see the patterns are the same. Same sort of ideas. Pierce, you all right? Okay, let's get into something interesting. Well, we've done some of this stuff. We've already done some of this stuff. Go back and look at this. Table 2.1, 21.1 I should say. We took these materials, alkynes, last semester, and we turned them into carboxylic acid by ozonolysis. We took we took primary alcohols and oxidized them. We'll do that again fairly soon once we have this Fischer esterification mechanism finished. And we made them into carboxylic acids. Then we did this. Nobody knows this mechanism. Did anybody work it out yet? No, I didn't think so. Okay. So this is magic. We get a primary alcohol going to a carboxylic acid. That's a very useful way of doing that. So we have made these things. Don't forget that. Now, here we go. Here you will push arrows like you've never pushed arrows before, which means hopefully in the right direction. That would be wonderful. We're going to see a lot of different outcomes here, a lot of different materials. But I would caution you that most of these materials are closely related. That's why they're organized in this chapter. They all contain this potential leaving group. So in this example, just FYI for right now, how do you make a carboxylic acid from a nitrile? This is just to exemplify the relationship between these materials. As you look at that compound, that looks nothing like a carboxylic acid. But to a chemist, that is a carboxylic acid. It's at the same oxidation state as the carbon in the carboxylic acid. If you look at this, let's say R is a carbon, and I have nitrogen, that's at a +3 oxidation state. If I look at the carbon over here, that's a carbon, that's neutral. 1, 2, 3. That's at a +3 oxidation state. That's why they're related. And the only difference between the nitrile and the carboxylic acid is water. You have to hydrolyze this nitrile to get to the carboxylic acid. And we'll do this mechanism in a little bit, not just now. We'll save it for later. How do we get there? We did this last semester where we took a cyanide nucleophile, attacked an alkyl halide, kicked it out, made a nitrile, and then hydrolyze. This is important. We'll get this in. So now you can do chemistry you've seen from last term, add it into the chemistry you're seeing now, and we can build quite complex products. That's useful. Other things we've seen, just to tie things together. Again, I expect to see people going, okay, that's fine, because it's the same stuff. We can take a Grignard, and we can react it with carbon dioxide. That's kind of fun to do. It's the dry ice material that you get. And dry ice is fun. You just drop it into your flask if you have a Grignard in there, and it will give you a carboxylic acid. And the chemistry is fairly simple. This is delta negative. That's delta positive. We've used those things as powerful nucleophiles quite a lot now. CO2 looks like this. I'd advise anybody who's in this class to know what CO2 looks like. It's got this internal sp carbon that's electrophilic, so we can go after it with a nucleophile. In this example, this is the Grignard. We're going after the central carbon. We're pushing electrons up onto the O. There's a carboxylate. All you have to do now from that carboxylate is to neutralize it by adding a proton, and you get a carboxylic acid. Nothing more complicated than that. That's it for the mechanism. I'm not doing any more than that for the mechanism. It's very simple. Start off here with a bromide. As you did in lab, make the Grignard experiment, make the Grignard material. If you had some dry ice and for your experiment, you put it in there, you get this carboxylic acid product. Add CO2. Now, what's this called at the last step? What is this? What's H2O plus doing? Quench. Now, let's be careful with that. Let's take a second to mention that. If I wanted to quench, I'll use the word quench. If I wanted to hydrolyze, I'll probably give you a clue, hydrolyze. Hydrolyze means a much more complicated process in which we're going to be able to go through maybe an acetal hydrolysis, maybe later on an ester hydrolysis. So I'll give you those clues. Sometimes in textbooks, they lump it all into one, like I said last week. They lump it all into H3O plus, and they expect you to know that all this stuff happens. I'll label it. I'll set it out so that you're able to know what's going on. Now, going back. So we're starting with the carboxylic acid, and we're going to use LAH. And this was a reaction last semester that really was kind of complicated. You can't do this with borohydride. Borohydride isn't strong enough to reduce one of these materials. So you need to use the nuclear option, which is LAH. And we can see here now the overall process is reduction, in which the carbonyl disappears. It has some sort of commonalities with things like reducing the dithiones last time, with the dithioacetals, somewhat like the Clemmensen reduction, somewhat like the Wolff-Kishner reduction. You're basically ripping this carbonyl out of here, or at least the oxygen, and replacing it with two hydrogens. Mechanistically, it's very different. Well, we've got to be careful here. Why are carboxylic acids kind of difficult to do? Why are they kind of difficult to reduce? And the answer is because this is an acid and this is a base. And if you put those two things together, you'll get an acid-base reaction. And whenever you do these reactions, you always see bubbles. And the bubbles are hydrogen gas. So that's because of the acid-base outcome. And that gives us this. Now, that's quite difficult to reduce. Why do you think this is difficult to reduce? If we're bringing in H-, why is a carboxylate slow to react? It's negative. You're bringing something negative into something negative. Well, it turns out mechanistically we can get around this. What's left over after this initial acid-base reaction is LaH3. What does LaH3 remind you of? Lewis acid catalyst. Great. Right? It's a Lewis acid. It can accept electrons. So mechanistically, the reduction here looks like this. Right? We can actually reduce the carboxylic acid down to an aldehyde, and then that aldehyde can get reduced down further. So in this example, that first reaction is the Lewis acidic ALH3 reacting with this carboxylate. Now, I'm not happy with this arrow. I'm going to sort of stop here for a second and ask you why I don't like this diagram. What's wrong with this arrow? It certainly does. It's showing a hydride attacking an O-. Yeah? If you've got the slides in front of you, I think that's maybe a little typo. So fix that. That arrow, my guess, is supposed to go there. Because that's the delta positive part. That's where it makes sense. And guess what? That's where it adds. So fix that arrow if you've got them in front of you. Or else it'll be confusing. What I've got now is this species. And if it starts to sink in, what does it look like? What does that remind you of? You've got a carbon in the middle with two O's attached. What does that remind you of? Hydrates, or something else related to hydrates? Acetals. Okay? They're the same, very much the same thing. So as we did with those compounds, we can expect some leaving to happen. We can expect the sort of this material closes and this breaks off, and that gives an aldehyde. So we've gone from a carboxylate salt and replaced the O- with an H to give, first of all, an aldehyde. It's exactly the opposite sequence of going from a primary alcohol through the aldehyde to the carboxylic acid. It's the opposite sequence. Down at the bottom, let's finish this off. Let's take the rest of the LAH and let's go after the aldehyde, because we know that's a very reactive species. And let's do what we've done in the past by adding H- to give the carboxylate, and then we quench it by adding an acid. That's the second step. We have to write 2 there. And that finishes it off. And you have to make lots of decisions. And that's the difficult thing here. Because in this first step, we're replacing something. We're replacing a group with H. So that's a substitution. And because it's on an acyl group and it's nucleophilic, it's a nucleophilic acyl substitution. What type of mechanism is this? Are we replacing anything or just simply adding something? Are we adding something or replacing something? We're adding something, right? This oxygen remains in the product, the H remains in the product, this H remains in the product. We have 2 separate processes on that slide. We have nucleophilic acyl substitution, NAS, and we have nucleophilic addition.